Hello everyone, my name is Farish Tani and my metric number is 97406. In this presentation, I will explain the main functionality of our code and run it to demonstrate its output. As you can see here, the round-robin function implements the round-robin scheduling algorithm. It processes the job based on their burst time and arrival time. Key calculations include turnaround time, which is the total time from a job's arrival to its completion, waiting time, the time a job spends waiting in the queue, finish times when a job finishes execution. The visualize results function generates two visual graphs. The first graph compares average turnaround time and average waiting time across different time quantum values. The second graph shows how the number of context switches or interrupts changes as we adjust the time quantum. These visualizations help us analyze the trade-offs of different time quantum values. In the main function, the program starts by asking the user to input the path to an Excel file. It validates the file to ensure it contains three required columns, which is job, burst time, and arrival time. So here, the program processes the job data for various predefined time quantum values. It uses the round-robin function to calculate metrics like turnaround time, waiting time, and the number of interrupts. For each time quantum, it displays a detailed table showing individual job results including finish time, turnaround time, and waiting time. Okay, let's start running the code. And then paste the path. You will get the figure like this. Here we have a graph analyzing the performance of a scheduling system across different time quantum values. Looking at the graph, we observe that the average turnaround time stays almost constant around 164,000 cycles. Similarly, the average waiting time fluctuates minimally, remaining close to 158,000 cycles. This indicates that varying the time quantum has little impact on this performance metric, suggesting the system is relatively stable regardless of the chosen time quantum. Then you can remove this, and then if it show another graph. This graph shows the number of interrupts across different time quantum values. This graph highlights that smaller time quantums improve responsiveness but cause more context switches, while larger time quantums reduce interrupts but may delay shorter tasks. Now let's briefly go through the table results for each time quantum. For smaller time quantum values, the turnaround time and waiting time are higher because of frequent context switching. The number of interrupts is also very high. And for the medium-sized time quantum, for example 20, as the time quantum increases, turnaround time and waiting time improve. The number of interrupts decrease significantly. With larger time quantum values like 40 or 50, with larger time quantum values, turnaround time and waiting time stabilize but may slightly delay shorter tasks, making the interrupts are very low but making the process more efficient. That's all for me. Thank you.
Good evening, madam. My name is Dylan Jais, and my matrix number is 98748. And today, I'm going to explain about the calculation results of the round robin of our code. And now, as you can see for the calculation results, there is the time quantum, the average turnaround time for each quantum, the average waiting time for each quantum, and also the interrupts for each quantum. So, for this function, it takes the job list, the best time, and the arrival time, and the time quantum. In this code, we start by creating a list called remaining time, which is a copy of burst time. This list keeps us track of how much time each job still needs to complete. We also initialize three other lists: turnaround time, waiting time, and finish time, all set to 0. This will help us calculate important metrics for each job. Next, we set a variable time to 0, which represents the current time in our scheduling process. We also initialize interrupts to count how many times jobs are interrupted, and the remaining jobs to keep track of how many jobs are still pending. Lastly, last job is set to -1, which will help us identify the last job that was processed. Here, we enter a loop that continues as long as there are jobs remaining to be processed. Within this loop, we start by setting a flag called job executed to false, indicating that no job has been executed yet in this cycle. Next, we iterate through each job using a for loop. For each job, we check two conditions. First, whether there is remaining time for the job to execute, and second, whether the job has arrived by the current time. If both conditions are met, we set job executed to true signaling that we are about to execute a job. Additionally, we check if the current job is different from the last job executed. If it is, we increment our interrupts counter, which tracks how many times the CPU has switched from one job to another. We then update last job to the current job index. Within our main loop, we still check if there are jobs remaining to be processed. After confirming that a job is available to execute, we now evaluate how much time it needs to compare to a predefined time quantum. If the remaining time for the current job is less than or equal to the time quantum, we can complete the job in this cycle. We update the current time by adding the remaining time of the job, set its finish time, and calculate both the turnaround time and waiting time. We then mark the job as complete by setting its remaining time to 0 and decrement the count of remaining jobs. However, if the job requires more than the time quantum, we only execute it for the quantum. We increase the current time by the time quantum, reduce the time for the job accordingly. And note that an interrupt has occurred since we may switch to another job next. After attempting to execute jobs, we check if no job was executed during the current cycle. If that's the case, it indicates that all currently available jobs are either busy or have not yet arrived. To address this, we need to move the current time forward to the next job arrival. We achieve this by finding the minimum arrival time from the arrival times list that is greater than the current time. This ensures that we skip ahead to the next moment when the job becomes available for execution. We then update our time variable to this next arrival time. After processing all the jobs, we return several important metrics: turnaround time, waiting time, finish time, and interrupts. These values provide crucial insights into the performance of our scheduling algorithm. The turnaround time indicates how long each job took from arrival to completion, while the waiting time reflects how long each of job went waiting in the queue. The finish time shows when each job was completed, and the interrupts counts reveal how many times the CPU switched between jobs. Following this, we have a function definition for visualized results, which is designed to take results of our scheduling algorithm and a range of time quantums. This function likely aims to create visual representation of the performance metrics, allowing us to analyze how different time quantums affect job scheduling efficiency. This function begins by setting up a figure for plotting with a specified size to ensure clarity. It then iterates over two key performance metrics: average turnaround time, average waiting time. For each metric, it plots the values against a range of time quantums, using markers to highlight the data points. The graph is titled performance metrics across different time quantums, with appropriate labels for the x and y axis, and includes a legend for easy reference. A grid is added for better readability, and finally the plot is displayed. In the second figure, the function focuses on the number of interrupts across different time quantums. Similar to the first plot, it used distinct color red to differentiate the metric. The graph is titled accordingly with label, axis, and legend, followed by displaying the plot. So, for this function, which is main, we use a method to put our Excel file so that the code can read what's inside the Excel file, what is the content of the Excel file. So if there's an error, it will show and file not found for the file path, or there was an error reading the Excel file. So the Excel file contains jobs, burst times, arrival time. And this code does not need to run multiple times for different time quantum, because the code is set to a time quantum range of all requirements, which is 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and 55, and also 60. Finally, for the last section that I'm going to explain, we loop through a range of time quantum specified in time quantum range for each time quantum we call the round robin function, passing the job details along with the current time quantum. This function returns 4 key metrics: turnaround time, waiting time, finish time, and also interrupts. And next, we calculate the average turnaround time by summing all the turnaround times and dividing by the number of jobs. Similar, we compute the average waiting time using the same method. This average provides valuable insights into how the choice of time quantum affects overall job's performance. And that's all from me, and I'm going to pass to my next member. Thank you.
Good evening, madam. My name is Dian Imu Lawrence, number metric 97359. Today I'm going to present about performance comparison of different time quantum. As for total number of interrupts, the number of interrupts decreases as the time quantum increases, as expected due to fewer context switches with larger time slices. As for time quantum 5, it has the most interrupts, which is 66,690. As for time quantum 60, it has the fewest interrupts, which is 5,556. Next, for the average turnaround time, the turnaround time is relatively stable across different time quantum, with slight increases for larger values of time quantum. The lowest average turnaround time is at time quantum 10, which is 163,652.03. As for the highest average turnaround time, it is the time quantum 55, which is 163,795.13. Next, for the average waiting time, the waiting time shows a similar trend to the turnaround time, with larger time quantum. In conclusion, the most efficient is the one that has the fewest interrupts and the fewest turnaround time and waiting time. For the time quantum that has the fewest interrupts is 60, and the fewest turnaround time and waiting time is for the time quantum 10. That's all from me.
Hello, now we will look into the chart showing average turnaround time and average waiting time. As you can see, the results aren't really that far apart. For minimizing turnaround time and waiting time quantum 10 provides the best balance of lower turnaround and waiting time. Next, we will look into the chart showing number of interrupts across different time quantum. Now, we can see that the results are really far apart from each other. We can see that time quantum 5 started out very high, and time quantum 60 has the lowest interrupts out of all time quantums. This makes it the most efficient, minimizing context switches with the fewest interrupts.
Quantum, since the primary goal for our project is to maximize CPU efficiency and to reduce overhead, time quantum 60 will be a better option due to its lower number of interrupts and acceptable average turnaround and waiting times. In conclusion, the best time quantum that we choose for our project is time quantum 60. And this is our team members, and thank you.